Welcome back, class. This is Whitlock and Schluter Chapter 10. We're continuing with our normal distribution. I want to move into some examples. And to lead up to it, we need to take a look at the table for the cumulative normal probability distribution. Let me show you how to use it. Go ahead and turn in your textbook to page 672. And there you're going to see this diagram. And what we're going to get in the table, I'm going to point, it's going to be these tail probabilities. So all the values in the middle of the table are those tail probabilities. And then the column here, it says first two digits of A dot BC, and then the second digit here, that is the number of the specific z-score. So for example, 1.96 is going to read 2.5%. That is this upper right tail region. So I come down here, look at 1.9 in the row, going to the 6 in the column, 0.025. To practice, let's just do a couple of them from the notes here. Probability that z is greater than or equal to 0. Well, let's sketch the diagram on the side here for that. That is z-score of 0, and it had better be 50%. So when I go look at the table, 0 is at indeed 50%. Okay, that's good. Now let's do number 2, probability that z is greater than or equal to 1. Okay, we'll just pop that one out here. 1 is going to be up here. If we use my 34-14-2 rule, we should have a 2 plus a 14 should get about 16. This is the number from the table. Let's see how it comes out. 1.0 is at 0.15866. So looking good there. Now we'll try z greater than 1.52. Okay. That was 1 right there. So for number 3, I'm just going to sketch greater than 1.52. So from the table, coming in here at 1.5, here's the 2.0646 is the correct number. So I go 0.0646. Relatively straightforward to read. 06426. Now, number 4 says probability z is less than negative 1.52. The table does not have negative values in the rows. Some tables do. Our table relies upon the symmetry of the curve, and so we're just going to use the fact that the results are the same on the left-hand side, but the values flip to negative. So while this right-hand tail is about 0.06, the left-hand tail going from negative 1.52 and left is the same probability. So I'm going to go ahead and just pop that right there. 0.06426. Now, what if we do number 5? The probability that z is between 1 and 1.52. I'm going to go ahead and sketch a fresh example here. But we already know 1, and we already know 1.52. Okay, 1.52 is about 0.06. The 1 was 0.159. Okay, so this dotted region will be the difference, and you can draw two separate curves and diagram it if you like. we could have the 1 minus the 1.52. And that's going to get this dotted region. So we're going to take 0.15866 minus 0.06426, which will yield 0.09440. So our probability is about 9% that you would be between z-scores of 1 and 1.52, or that many standard deviations away from the mean. Lastly, probability z less than or equal to 1.52. You can imagine that we're going to use the fact that we already know that 1.52, but since we're doing less than, we shade left. The area under the whole curve is always 1 or 100%, and so shading left, I'm just going to do 1 minus 0.06426, and so we'll obtain 0.93574. Okay, now we can also use the table to answer the question for Aaron and Miriam, and since Aaron was at the 2, his percentile is going to be found by 1 minus the value I read from the table on the 2, and Miriam's is going to be 1 minus the value from 2.29. So let's just go to that table. For 2.0, it's 0.02275. For 2.29, we obtain the number here, 0.01130, and so we can see that those numbers are lining up about 98th to 99th percentile, roughly. Lastly, I give scripts here which show how to obtain the cumulative normal probabilities using R. The command is called pnorm. P stands for cumulative probability. Norm, of course, is normal distribution. The syntax for these types of functions, the same function for the binomial probability distribution we did binom, is x in first position and then the mean in the standard deviation, second and third. Okay, I'd like to do a couple of examples. So, first example, we have this World Health Organization study in various countries has a true mean of 121, standard deviation 16. So thinking in my population here, the mean is known to us, standard deviation is known to us. This is not always the case, but here we are. 140 is considered high blood pressure. So, first question, what's the z-score for 140? No problem. We're just going to take our formula that we had written before, which is the statistic minus the population parameter for the center, divided by the population parameter for standard deviation. And in our case, we have 140 minus 121 over 16. That gives 1.19. Now, if this variable blood pressure is normally distributed, which in the populations I've looked at, blood pressure does tend to be normally distributed, then we can calculate the proportion of Canadians that suffer from high blood pressure. So, we're going to let x follow that normal distribution, and we simply want to know the probability that are over 140. Okay, so mean again is 121, and we're going for this 140, which we know is a little bit more than 1 standard deviation above the mean because of our given z-score. So this level is x, and this this level is z. Percentages are the same on both. Z-score for the mean is 0. Z-score for 140 is 1.19. Therefore, we shade on the right-hand side because we want greater than or equal to 140. A direct table read is going to result in 1.19 right here, 0.11702. The 9 is the last column. Okay. So 0.11702. Thus, about 11% of Canadians suffer from high blood pressure. One more example. Oh, one piece before that. What proportion are not classified as high blood pressure, but in the range 100 to 140? So to do that, we need a z-score for the 100. So we'll just quick z-score again is going to be the value you're looking at minus the mean from the population over the standard deviation. That's going to get us a negative 1.31. So on the curve, we're looking at, let's see, 100 is below the mean, so over here, and the 140 was above the mean here. So we had 1.19 on the z-score, 2 minus 1.31, and I want that entire shaded region. So to get that region, we're going to have to subtract. We've got this 1.19. That one gave us 11.7%. So I need probability that z is less than or equal to 140 minus, you know what, let's do it this way. Well, that's fine. Minus probability that z is less than or equal to minus 1.31, which I've obtained. So, let me write that one over here. 140 would be 1 minus 0.11702 minus 0.0951. And the arithmetic on that, 0.7879. Okay, so we're looking at approximately 78 to 79% of Canadians in that blood pressure range. Okay, last example. We're going to switch scenarios to some type of manufacturing process. Very common to see these kinds of applications. In this one, we're going to have a hopper car loader putting coal into cars. Calibration is set to have an average of 75 tons of coal and standard deviation 0.8 tons. So, notationally, we've got X normally distributed, where X is tons of coal loaded into the car, with mean 75, standard deviation 0.8. We want to know, for our particular coal car, we only came up with 74.5 tons. So we're half a ton short. What's the probability of that? Did we get ripped off, or is that just going to happen sometimes? Well, here we go. 75, I'm going to put 74.5 over here on the left. Doesn't matter exactly where you put it. Of course, the more accurate your sketch, the more it helps your intuition, but before you solve it, you don't know exactly where to go. So, probability that X is below 74.5 is the same as the probability that z is below what? So z is 74.5 minus 75 over, what was the standard deviation? 0.8. Okay, so we've got minus 0.63, rounding to 2 decimal places because we're using the z-score. Now, probability that we're less than on the left side of the curve means we can do a direct table read. So here's the 0.63, 0.26435, 0.26435. Okay, so there's about a 26.43% chance that we would get shorted a half a ton of coal. So that's going to happen sometimes. Okay, now I have one more piece on this question and then we close. So let's suppose that we go in the reverse. You got a coal car load that was in the 10th percentile of all loads. Whether that was you, maybe your child got the 10th percentile on a standardized exam. Whatever, if you start with a percentile, can you go back and find out what the score was? Yes, we can. So the way that we need to do it is we're going to invert our formula. So we started off with this. Z-score is stat minus parameter over standard deviation, or x minus mu over sigma. If you solve for x, you're going to come up with this. You might try it. So we can simply use that formula. So we're going to read the table backwards. If the z-score was 10th percentile, I'm going to look through here and I'm going to see where is 10%. So I'm fishing around. Here's 20s, 30s, 10s, 12s. Okay, there's a 10. So now let's go and find, that goes to 11. And go to the right, 10, 10, 10, 10, 10, 9. So somewhere between these two, 1.28 and a 1.29. The 1.28 is closest, so we will use that. Now, I want to be very careful and sketch the curve so that we pull out the right z-score. 10th percentile is small, which means it's on the left side. So I'm going over here on the left side, and I need a negative value. So positive 10% would be here at 1.28. 10% on the left is going to be minus 1.28. So the z-score I need is minus 1.28. And I'm going to plug in my mean and my standard deviation with the z-score here and here to obtain roughly 74 tons. So 74 tons is at the 10th percentile of coal loads, and we've got it.